Welcome to a new episode on the Technomora channel. We really hope you will enjoy watching it and invite you to tell us what you think of it by leaving your reactions below the video. And now, please allow me to present your host, Technomora.
Thank you, Julie. And now for the weekend project. Now, a while ago, I realized that to understand how something works, you actually really need to try to make it. Now, every self-respecting electronics enthusiast will encounter at one time or another in his, let's say, career as a electronics enthusiast, the need for a power supply. Now, nowadays it's as easy as going on eBay or Amazon or Craigslist and buy a power supply like that one, yeah, and you're done. But if you do that, you still don't know how it works. Anyway, my goal was to make a power supply which is simple, effective, and does, let's say, just a little more than what a comparable commercial power supply would do. And let's say, in the spirit of the philosophy of my channel, I wanted it to be cheap, simple to build and maintain, and reliable for anyone to use. Now, a word of warning before I go on. So let's say this is the health and safety section. I did all the prototyping and experimenting on my workbench, and you can see there are a lot of wires running every which way on my bench. Now, I know what I'm doing, okay, and I know the risks involved, and I do this so that you don't have to do it, alright? So either way, if you're going to follow after me and build your own power supply, whether it is exactly the way I built it or whether it's your design, let's say, be warned, there are a lot of high voltages and high currents involved in this, okay? It might not kill you, but it will certainly hurt you. Never ever build a prototype like I did without at least using a separation transformer, the thing you see there with the voltmeter and the current meter. So now it's set currently at 225 volts AC output, and there's little or no current running through it, alright? And on top is my variac, that thing with the big knob on top, yeah? And that sets the output voltage that I will ultimately send through the transformer of my power supply. This transformer has two secondaries, two separate secondaries, which can each deliver 48 volts AC at 1.25 amps. Okay, that is quite a bit of power running out of this transformer. Alright, and then the next dangerous thing, if I haven't put you off just yet building your power supply, are the filter caps, the electrolytics, which filter the power. Needless to say that all the wiring you see here, by the way, is not suited to carry 1 amp. Alright, at most they can take maybe 100 milliamps. But this is only a prototype board. So So obviously the final design will have the appropriate wiring. Anyway, the filter caps you see here are rated at 3300 microfarad. Let's see if I can show you. There. Alright. And at 63 volts. Now, remember, once your power supply is running, these caps are being charged up to full capacity. If you're going to short these caps, their leads, whether with your fingers, and I hope you won't do that, or with some tool, some metallic tool, you're going to have a huge spark. Yeah, and if you're unlucky, you might even explode the electrolytic. So be careful. Alright, so the output of my power supply is currently set at outputting 53 volts DC, either negative here or positive over there. If you're going to work with this power supply, take your precautions and keep your eyes on the business. So I know most of you by now are curious to have an idea how the power supply schematically looks like, and this is it. Alright, so I could explain the schematic and how it functions as it is with the prototype here. Alright, but that would, I don't know, that would be a little hard to do because there's really no order on this board, and it would simply be far harder for me to explain it to you. So what I'm going to do first is show you a few voltages, and once the board, well, the components I should say, are transferred to their PCB, then I will explain to you in a little bit more detail how the power supply works. Alright, so the board is now switched on, and the input voltage gauge, which is this nifty little display here, is indicating right now the input power to the transformer is 220 volts, 50 hertz. No current is being drawn, or practically no current is being drawn, so it indicates 0. Now keep in mind, this little display here is not it's not extremely accurate, and neither is it very sensitive. It's just there to give you an indication of the fact that the power supply is running. Actually, so you know, I use this as a pilot light, or you could say an on-off indicator, and at the same time displaying a few useful informations on the power going into the power supply. I bought this for a few dollars on eBay, but I don't remember exactly what I paid for it, but I think it was in the region of $8, if I'm not mistaken. Either way, if you look around on eBay or Amazon, you might find a similar indicator. So both outputs right now are set to 0. So at the top there you see the output of the negative channel of my power supply. At the bottom you see the output of my positive channel. Alright? Now both channels are coupled to a load, meaning a power resistor on that little board there. Alright? So I'd advise you to always run this with a minimal load, which is anywhere between 450 ohms, 5 watts, or up to easily 3,300 ohms, 5 watts. Alright? So, yeah, just hook up a little load to the output. It's safer. Alright? Now anyway, as you can tell, the output of the negative channel has a slight voltage there, yeah, and we're in the millivolts range. So actually there's a slight leak of 900 microvolts. Alright, so not millivolts but microvolts. I attribute that first of all to all the wiring you see running here, and not less than ideal electrical contacts, which have a slight resistance, which might influence this tiny voltage leak of 900 microvolts. In fact, I expect this to become 0.00000 once the whole breadboard will be transferred to the PCB. Now, the positive output measures effectively 0 volts. Alright, so there is a power resistor, a 5 watt power resistor hooked up to the negative, and that's this one here, which is a 2200 ohms 5 watt resistor. So one warning though, if you're going to run your prototype without any heat sinks on the power transistors, and you see the power transistors there, alright, do not load them down for longer than a few seconds. And when I say a few seconds, at most 5 or 6 seconds, alright, under full load. Because these things really start to heat up once you start to draw current, and especially if you send the maximum voltage through them, like 50 volts or so. Alright, so if you're going to test it without heatsink, never load them down for longer than a few seconds. So as I said before, this one indicates the output voltage on the negative channel and the current running through the load, which is hooked up to the negative channel. Alright, so I'm just going to give you an idea of how it reacts when I turn up the potentiometer to set a certain voltage. But mind you, I won't be able to let it run for a very long time at maximum voltage. Alright, so I'm going to turn the potentiometer for the negative voltage output right now, very slowly up and back down. There you go. Okay, we're at full voltage. So you see minus 53 volts at 20 milliamps. Alright, so my goal is to calibrate it to not more than 53 volts. Alright, so theoretically I could go probably as high as, I'd say, 54 or maybe even 55 volts. But yeah, I think if I set it to 53 volts, that will be more than sufficient to restore any vintage equipment. Yes, you need to build a heatsink. You need to build in your power transistors into or onto a heatsink, okay? Because that's going to dissipate a lot of heat. Alright, so now I'm going to show you the same thing for the positive channel. Let me show you. So there. Now you see the multimeter for the positive channel. Alright. It has a load which is slightly lower, which is I think 450 ohms at 5 watts. So there you go. And remind you, this I can really only do for a few seconds and then I need to stop. So there you go, 52.9. What you're seeing right now on your screen is the scope which is hooked up on the positive output of my power supply. Yeah, and right now I'm set at 100 millivolts peak to peak per division. Alright, I don't know if you can see, if I can show you the scale illumination. Yeah, you can see the scale there. Alright, so right now it's set at 100 millivolts peak to peak per division. Alright, so I'm going to turn down the sensitivity. Let me show you there. So the sensitivity of the input of my scope, and I'm going to show you what the result is on the screen. Alright, so right now we're at 100 millivolts per division. This is 50 millivolts per division. This is 20 millivolts per division. This is 10 millivolts per division. Alright, so 10 millivolts peak to peak. In fact, the signal is so weak the scope is having trouble to lock. There you go. So this is 10 millivolts peak to peak per division. So that's the how to say, that's the ripple on my power supply's positive output. Alright, so let's go down to 5 millivolts per division. Alright, this is 5 millivolts per division. Alright, so let's see if I can turn up the luminosity a little bit, so maybe that would be clearer to you. There. Alright, as you can see, the 50 hertz ripple is pretty well contained, but there are quite a few transients in the voltage. Now, try as I may, I never completely succeeded in eliminating these little spikes you see at the top of the current. Alright, I'd much appreciate any of you guys giving me a few suggestions on how to reduce even those. I've tried with several filters, and this is so far the best I've managed. It's still not bad, really bad. I mean, mind you, this is at 5 millivolts peak to peak. Alright, so if I push it up a bit, so with the transients it's at about 10 millivolts peak to peak, yeah, of ripple. So if I go to 2 millivolts, yeah, that is a large ripple. Alright, so that is a large ripple. Okay, so I know you see some artifacts on your screen, but that has to do with the difference in shutter speed between my camera and the screen, the actual screen. Alright, so now we're at 2 millivolts peak to peak per division. Yeah, so let's go back to 5 millivolts peak to peak. Now the output voltage right now is 0 volts. So I'm going to push up the power supply, the positive, to say 10 volts. But mind you, I can't do that for very long because there are no heat sinks on the power transformer. So here we go. Okay, this is about 5 volts. This is a little bit more than 10 volts. So this is 10.36 volts to be precise. Okay. So yeah, you see, as soon as I take the potentiometer, or as I put the potentiometer down, you see that the ripple diminishes immediately. Now look what happens when I touch the case of the potentiometer. You see that? So my body functions as an antenna which picks up the 50 Hertz ripple all around me. Yeah, there. You see. So it's imperative when you build in your device into a case that the case is metal and that the potentiometer is shielded from any human contact, alright, or any outside contact. Because as you can see, that induces a lot of ripple onto the output voltage. Okay, let me turn it back to 0. Alright, so that was 10 volts. Now, the ripple has a tendency to get a little bit bigger at a certain voltage, I would say maybe around 37 volts or so, and it gets up to maybe 15 millivolts peak to peak. Alright, and once I get to maximum voltage, it drops back to around about 5 millivolts peak to peak. So yeah, right now, of course, with the camera running, my multimeters running, the scope running, my lighting, which is LED all around me, well, you can tell there is a ripple, and we're now at the 5 millivolts per division setting. Okay, so right now the ripple on the DC is 5 millivolts peak, 10 millivolts peak to peak. So, which, all things considered, with all the equipment running around me, yeah, is not too bad. But yeah, it's not perfect, so maybe I can make it perfect in the near future. Alright, I gave you a very short demonstration of what the power supply can do, but I think now the time has come to transfer everything to a PCB, and maybe then I can explain a little more on the design of the power supply. Alright, you know by now that this is only the first part of the project. I'm going to build a few more, let's say, parts for this power supply in the future, in the near future. And it is my intention to build each of those parts that I want for my power supply with extra functions, let's say, on tiny little boards like these. Alright? One board will contain the bridge rectifiers and, let's say, the power caps, and that's about it. The other board will contain all the other parts you see right here. Alright? And so forth. So every separate function of my power supply will get its own little board. And the advantage of doing it this way is that I can expand my power supply with new functions, or even replace an old board with old functions by a newer and hopefully improved design. I know it's a bit early to talk about the case that I will use for my power supply, but even so, before I start building it, or before you start building it, it's always a good idea to have at the form factor and the shape and depth and material of the case you're going to use. And as it is going to be fanless, so remember, I want a silent power supply, an adequate heatsink for cooling the power transistors and the power resistors that will be placed or connected to my power supply is essential. And I went to the local scrapyard and I found this aluminum box, and it's quite thick. It's thick and heavy. It's about, I would say, 2 millimeters thick, and it's quite deep. And what this was, it was the case of an external CD-ROM writer, and I gutted it of its content, and it turns out that actually it has a tray which fits right into the housing, which makes my life even easier. And by the way, I had a look at how the transformer would fit inside of it, and I've got plenty of space for the transformer. As you can tell, the transformer will fit inside perfectly. Okay, let me give you a look of the insides of the box and show you my reasoning, or explain to you my reasoning. So inside the metal case, the aluminum case, you can see these rails here. All right, and this tray is steel. It's just plain galvanized steel, and it sits on top of the rails like this. All right, so it can slide in and out through the back of the box. Now, my plan is like this. I'm going to place, I think, the transformer in the central location, right at the back of the tray. Something like this, maybe, or maybe like that. I haven't decided yet. Obviously, the power cable will be located, well, either here or there. I still have to decide that yet. The power switch, on the other hand, would be at the front. Alright? As would be this indicator. So, or the gauge, I should say, or the pilot lamp, so to speak, would sit at the front like this. Alright? So, and then I would place a power switch at the front, and I think I will use a classical toggle switch like this. Although I have to confess, I prefer the aesthetics of this switch, which is an on-off double pole switch. Right? This switch is also a double pole switch. But unfortunately for me, the front real estate of the device is rather small. And as I told before, my power supply will consist of several modules. So I'm not sure yet, and each, well, some of those modules will have their own outputs, and all those outputs must fit within this little window, alright, together with the power switch and the indicator and everything. So yeah, I'm limited, like I said, by the surface, the available surface on the front panel of my power supply. So unfortunately, although this switch looks aesthetically more pleasing, it's stainless steel, by the way, this switch would make more sense, and it's cheaper too. So remember, I'm trying to design something that some of you might want to build as well, and I try to keep a tight constraint on the cost of building this power supply. So yeah, I don't know, what would you do? Would you use this and lose precious space on the front for other connectors and possibly switches? Or would you use the sensible option, a smaller switch, which uses less space on the front and leaves more open for other functions, future functions? I don't know. Obviously, I mean, I could build a new front panel if new functions would be added, but I don't think I'm tempted to do that. But either way, I must sleep on it. Now, I'm going to use a stainless steel front panel. Alright, I bought already a nice 2mm thick stainless steel piece of steel, which I can cut and then make fit right inside this little window here. Alright, so that will look nice. Now, about the modules of my power supply, let me show you. So, oops. So, let's go for the sensible option first. So, like this. Alright. So, suppose I do, as I said, I would build the transformer inside the case there. Then at the front you would have the indicator, the switch, one above the other or next to each other, I don't know yet. And then a whole slew of output jacks here, and maybe some switches above it, I don't know yet. Anyway, so right now you see the amount of space I've got left to build in modules. And as I said before, I'm going to build modules on these 7 by 5 centimeters little print boards. And if I place the print boards vertically like this next to each other, yeah, and I leave enough space on the left and on the right of them, say I would say 1.5 centimeter on each one, then I could place, roughly speaking, 1, 2, 3, 4, 5, possibly 6 of the modules next to each other. And I think 6 modules for the functions I've got in mind would be ample. Having a look first at the case in which you're going to build your parts allows you to sort of plan for the building of the print boards. Now, keep in mind I'm going to use these perf boards for now to build my power supply, but I hope in the near future to make my own print boards. Either way, the placing of the components is rather important, because as you saw, I need to be able to place the boards. Well, first of all, I'm going to place the boards vertically like this, alright? And the space above and next to the boards is, let's say, sufficient, but not to such a degree that I can waste the space. So I need to think carefully how to put together each board. Okay, so it's definitely not a useless exercise to have a look at the case first and to sort of place your parts and have a look at what sort of space they need to be built in. So I don't know yet. Actually, I'm still doubting whether I should place my boards vertically inside the box or whether I should place them horizontally like this. Yeah. If I place them horizontally, I could stack them with standoffs, so that would work as well. So I'm still sort of thinking what would be best. Alright, I just finished the power supply rectifier bridge brick, so to speak. So this is where the AC of both secondary AC coils will be connected to from the toroidal transformer over there. And and you see the 2 bridge rectifiers here, and then the 2 filter caps which are connected to the bridge rectifiers, and then you see 2 small resistors bridging the wires of the electrolytics. Okay, and these are 820 kilo ohms, if I'm not mistaken. Let me check. 800. So these resistors are 820 kilo ohms, quarter watt metal film resistors, which are soldered over each capacitor's legs. All right, and their only function is to discharge slowly the capacitors once the power supply is switched off. Yeah, such that there isn't any residual electric power left in these capacitors. Just for safety's sake, and if somebody, me or somebody else, needs to maintain, or repair the power supply, then at least they'll be safe from shock. Yeah, okay? So there you go. The whole thing is well, mounted and wired, ready for use. So now I need to transfer the other parts to a separate function board. Now some of you might wonder, why am I using white wire and color coding it with some shrink tubing instead of using wire which is already colored with the appropriate color? Well, for the simple expedient reason that I only have one roll of silicon insulated, heat resistant and high voltage resistant wire, and it just happens to be white. This is wire of 0.75 square millimeter section. Alright, now don't ask me what type of gauge it is, but if I make a guess, this is probably 16 or 14 gauge wire. Just a quick update, I finished the positive channel of the power supply, and this is the underside of the print board. Alright, so yeah, I placed all the parts for the positive side. All I need to do now is do the same thing on that side of the print board for the negative side of the power supply. You're looking through my magnifying glass on the workbench. So I'm making the connectors for the potentiometer, okay, and I'm soldering them under the magnifying glass because those parts in reality are really very, very small. So just to give you an idea, this is without magnification, and this is with magnification. So yeah, if you got good eyes, I suppose you could do it without a magnifying glass, but even so. Anyway, I'm going to connect my potentiometer with coax wire, thin 50 ohms coax wire. And the reason for that is that I want to avoid to introduce any kind of stray signals into my power supply. Remember those spikes we measured on the oscilloscope? Well, yeah, I want to exclude any possible source of stray signals, spikes, noise, etc. Alright, I hooked up the potentiometer to both wires, and as you can tell, I soldered the shielding of both wires together and to the case of the potentiometer so that it is also grounded properly. Then I connected both wires to the little connector over there, and right now I'm checking the resistance overall on both ends of the potentiometer, and it's close to 100k for what it's rated at. So what I'm going to do now is I'm going to connect my multimeter to the wiper connection in the center here. There. Alright. So it's measuring practically zero, so that means the wiper is at one end of the potentiometer. Now if I turn the potentiometer, it should react. There you go. So yeah. Alright, so the potentiometer seems to function normally. Yeah, my multimeter is reacting a bit erratically lately, but I think it has to do with the fact the battery is almost empty. There you go. So yeah, the potentiometer is hooked up. So now we can move on to testing the positive side of the stabilized power supply. So in effect, this side of the power supply. Alright, I hooked up my the positive side of the power supply of my power supply to my bench power supply, and remember this power supply can only deliver for the moment 23 volts. There's something wrong with it. I need to look at it, but it seems only capable of delivering about 23 volts for the moment. I think there may be a short inside. Anyway, it's sufficient to do a test. So I'm going to pump about 23 volts through the positive side of the power supply, and I'm going to vary the potentiometer and see whether this affects the output voltage, in fact, of the power supply. Alright, so mind you, like I said, it's at reduced voltage, so the Zener diode reference voltage on the PCB won't kick in. So the only thing we'll be able to check, in fact, is to see whether the drive transistor, which is this one here, allows to drive the output transistor. Okay. So yeah, it's only a cursory test, but just to see if it functions normally. So here we go. Alright, so 0 volts. So now it should react if I turn the potentiometer. There you go. So I'm injecting 22.5 volts positive, and I'm varying the voltage with my potentiometer. Alright, so now it's at 0. Remember, there's no load on the output of the PCB, so the voltage will react and drop back to 0 eventually. So yes, there you go. The positive side is built. It's tested as far as I can test it with this setup, but I'm reasonably confident there are no errors in it. So all I need to do now is build the negative side of the power supply and then test it, and then we're ready for part 1 of building my ultimate, you could say, power supply. Alright, the part 1 of my power supply is built, and I'm going to show you the result of the building in a moment, but I need to give you a few more, let's say, tips if you're going to follow along with me and build your own power supply based on what I am doing. You must be warned that this power supply is full of high voltages and high currents. Alright? So if you're going to follow along with me, be aware of the risks involved. Alright? So there you go. Now, a few tips for some of you who might want to build the same type of power supply that I build now. First of all, you do need to take a Zener resistor here, which you see here. You're looking at the positive side of the power supply, alright? So, to make the Zener function correctly, because this, in the end, this combination of resistor and Zener diode is your voltage reference, alright? And this is in fact what is going to stabilize the power supply, alright? So, this resistor here is crucial. This makes the Zener diode conduct sufficiently and does allow through enough current for setting the transistor, the driver transistor, which ultimately will drive the power transistor, which, by the way, is a Darlington transistor. Alright? And this, so therefore, this Zener resistor combination is the heart of the design. If you take too low a resistor, the Zener will pass through way too much current and will become very, very hot. Alright. If you take too large a resistor, the Zener will never start doing its job of limiting the voltage. Alright. The Zener does need a certain amount of current, albeit a tiny one, to do its job. Now, I tried with a 2700 ohms, so 2.7 kilo ohms, and it worked, but the Zener became really, really hot. Alright? And therefore it was drawing way too much current. So I did two things. Instead of using half a watt Zener, I used a 1 watt Zener diode, and I nearly doubled this resistor here to 5.6 kilo ohms. Alright? And that seemed to have done the trick. The Zener didn't become nearly as hot anymore as it did before, but it did its job perfectly. So it became warm but not hot, and the voltage it gave off was rock solid stable. Now, do bear in mind that the output of the transformer, alright, is 48 volts, 1 amps, alright? At least that's what it's rated at, alright? So, after the bridge rectifier and after the filtering of the power, the power climbs up, or the voltage, I should say, climbs up quite steeply. Alright, so voltage is close to the 65 volts DC is not exceptional, after filtering. So, therefore, the Zener diode and the Zener were selected to work properly with that kind of voltages. Alright, if you're going to use another Zener and resistor combination, you have to calculate your own Zener diode. Alright, I'll put a link down below the video where you can find all the proper calculations to do that. But even so, even if you calculate a value, you will notice that in practice it's much harder to find the exact right resistance for this resistor here. Alright, because the point is you need to give the Zener diode just enough current so that it doesn't heat up, but it does what it needs to do, but not let through too much current that it explodes. Yeah. I did use two TIP 131 type Darlington transistors for both the driver and the limiting transistor, yeah, which is overkill. I mean, at least the driver transistor doesn't need to be a Darlington transistor, but I went for easy. No need to find all sorts of types of transistors, just the same type will do. If you use another transistor, say, I'm just suggesting, a BD139, it might be a few cents cheaper and the transistor is a bit smaller, but it might do the same job as using a TIP 131. Alright, now a few more things that are critical, but that would seem details, is you need to keep the leads short between components. Alright, so normally, of course, I would design a PCB with copper traces and then use that. But since this is, you could say, a working prototype, I built it on a perf board like this. So if you're going to do the same thing that I built, yeah, if you're going to build, let's say, a similar power supply, you need to keep the leads on your perf board as short as possible. And of course be aware that none of the leads short with each other. Alright? So the reason for that being that the longer the leads are, the more chances are that you'll introduce some stray signals into your power supply from the outside, yeah? Because every lead functions as an antenna. So there you go. Those are, I think, in the main, the best tips that I can give you. Of course, you know, be aware that these transistors, these power transistors, will be attached to a heatsink. So if you're going to test your design, you know, never ever send full voltage and full power through the transistors without heatsink for more than a few seconds. Okay, and when I say few seconds, I mean 1 or 2 seconds. These transistors, as rugged and as strong as they may look, if they need to radiate, say, 50 watts of power through a tiny little metal back like they have, forget it. They're going to blow immediately. Alright? So there, if you're careful and you build everything meticulously and you check and check again, you might end up with something like this. So back here you have the bridge rectifier and filtering module, and this is the regulating and variable part of the power supply, alright, with its potentiometers, which are connected to the main board, you could say, via a 3-pin connector. Alright, and those 3-pin connectors for the positive side go here, for the negative go there. And there is also some filtering on this main board, you could say, which is actually a tiny board of 5 by 7 centimeters. Alright, let's say for the American viewers, 2 inches to 3 inches. That's about the size of those boards. And then I went the easy way and I bought this little gizmo here, which will allow me to see the incoming voltage on the transformer, alright, on the 220, let's say, and to see the frequency of the AC and the current running through the transformer. I see this more like, you could say, a pilot light, just to show that the power supply is functioning, rather than something incredibly useful. But you know, I just thought the eye also wants something to enjoy. So there you go. There are still a few more considerations to make. What sort of knobs will I use? This is the front. Yeah, so at the back here is the solid aluminum case into which the power supply will be built. I'm still thinking about the design of the front panel of the power supply, so I don't know yet what its look will be, but yeah, I need some time to think it over. Now, if you have suggestions, of course, by all means, write your suggestions beneath the video, and I'll see whether I can gather anything useful from those comments for, let's say, part 2 and possibly a part 3 of building my own ultimate power supply. You know, there are many more new functions to be added to my power supply, and each function will be built on an exact same little perf board like you see there, so 5 by 7 centimeter perf board. And obviously I will show you those functions as I build them, and tell you how to build them yourself if you should wish to do so. So there you go. I would say thank you for watching, and I'll see you for the next video in a few weeks.